good to see everyone's saying hi in the chat already. So welcome to one of the first workshop of 2022. I am Simon Foster from Surface Ventures, and I will be beginning the first part of this talk covering the theoretical aspects of wettability before we hand over to Dr. Sebastian Schalbach from Data Physics Instruments. Sebastian, would you like to say hello to everyone?
Yes, hello, and a very warm welcome also from my side. So today what we are doing is we show you a little bit how our tensiometers are working, and we show you how to measure so-called imaginary contact angles on tooth implants as a substrate. So I'm very happy. I already read the list of participants, so even some people I know. So you see the world of surface chemistry is quite small, but very, very interesting. And this interest I want to share with you today. So see you again in a moment.
Brilliant. Thanks, Sebastian. Right. So good that you all said hi. It'd be nice to see where some of you are joining from. If you'd like to write that in the chat as well. So just a reminder, this is a workshop session. So with this, please do ask questions in the chat. We do have a couple of Q&A sessions scheduled, one just after my section of the talk. So myself and Sebastian will try and answer any of the questions relating to the theory that you may have. If there's anything I can answer when I'm going through the talk, I will try and do that. And then we'll have another one following Sebastian's demonstration of the Tensiometer platform. So with that, I will be trying to facilitate the Q&A as he operates the machine and shows you how it all works. So let me just bring up my slides just one moment. Okay, so as you're all aware, wettability specifically focused on hydrophilic surfaces and imaginary contact angles. So what we'll be covering is some of the fundamentals of surface chemistry. I'll give you an overview of wettability and contact angle analysis, talk about tensiometry for the measurement of surface and interfacial tensions. And then following my presentation, Sebastian will be, of course, demoing the tensiometer. Before we kick off properly into the presentation, I have some poll questions that I would like to release. There's a few of these. So I'd like to start with just finding out a little bit about you, specifically where you're at in your career, if that's okay. So I'll share that now. Please go ahead and type those answers in. While we're doing that, I'll just start reviewing some of the definitions that we have. So what is surface chemistry? In this, it's a special field of physical chemistry, and it's the study of chemical reactions that occur at interfaces between two phases. So there can be a few different phase interfaces. Some of the common ones being, and most of these being, solid liquid. So typically this is liquid contacting on a surface. Solid gas, solid vacuum, liquid gas, and liquid liquid. You can have, of course, two dissimilar liquids interacting. So that's something to be aware of, and something that does crop up in some tensiometric analysis methods. So this requires an understanding of the composition and properties of the interfaces between these two different phases, or two different volume phases. Continuing on with some of these terms, a volume phase is a region without any erratic changes in physical parameters. Phase boundary, so this is where we have two immiscible volume phases in contact with each other. So as I've talked about in previous workshops, and as some of you may remember if you've attended some of our other ones, more focused on specifically modifying and engineering surfaces. A surface is quite a complex thing, and the interfaces between them aren't quite as discrete as what we would like them to be. So the interface is generally expanded across several atomic layers, with continuous changes in the physical properties between different volume phases. The interface itself, we like to think of this as an idealized, infinitely thin phase boundary. So you can just so in terms of modeling, we could just say, okay, the atoms of one phase extend up to here, and then from this phase onwards, they would extend up to the next phase, whatever that may be. And then a surface itself, we can think of as a special case of an interface. Basically a condensed phase, typically either a solid or liquid, contacting a gas phase or an absence of gas, that being a vacuum. So now I'd just like to release the next question, just asking about area of expertise. So continuing on from there in terms of surfaces and interfaces, we can think of these in terms of particles at interfaces. So we have, and also in terms of the forces between those. So essentially at an interface, the particles have fewer direct neighbors than the bulk. So if we think of a bulk crystal, any of the atoms or molecules of that or ions of that crystal will be surrounded by other atoms or molecules or ions, which will have bonds between them. So effectively, those have more bonds, whereas at the surface there are fewer and also weaker bonds. So in order to bring bulk particles to the surface, you would have to break those bonds, and this would require energy input into the system. So with this, we can kind of think of for the bonds between things in bulk, we instead have what are called cohesive forces, essentially the forces holding this bulk phase together, whereas the forces acting between different phases or between something that is adsorbed onto a surface, these are adhesive forces, so between two dissimilar things. So with fewer surface particles, you would effectively have lower surface energy. We'll talk a little bit more about surface energy and its definition in a few slides, but effectively, and we'll talk about some of the thermodynamics of this, surface energy, effectively, your systems want to minimize surface energy. And we can think of this and come on to talk about this in terms of surface enlargement. So increasing the energy of the system by enlarging that, we do work on the system to actually, so we have our sort of imaginary phase here that we are increasing by size ds using a force F. And this requires work or change of work, delta W, to change the area. So with that, we have to do work on this, and this then would change the interfacial tension. So with that, that's the interfacial tension, definition-wise, is the change of or delta W divided by dA, change in area. So the work done or energy inputted into a system for the enlargement of the interface between two phases for a specific unit. And that gives us our interfacial free energy. So our sigma being our surface energy, but we use a specific, use this gamma symbol specifically between two interfaces, between a solid and a liquid, or a solid and a gas. A special case of this, the surface tension or surface free tension, as applied to liquids, whereas we use surface free energy to talk about solids. Again, we'll talk a little bit more about this later on. In terms of surface tension, so we can think of this in terms of some analogs. So you have a one-dimensional, that being a tensioned rope. So effectively we have only one dimension. So if you're pulling on that, the forces are contained only within the rope itself. Okay, whereas if we have a 2D tensioned area, there is that across the areas. We can see there is sort of a sheet, this little diagram, or we can think of that like a trampoline, effectively, where we have balanced forces between the surface tension and the external forces keeping it taut and applying tension to said trampoline. I do this. I'd just like to add another question there, if you all don't mind answering. Thank you. And then we can have a 3D tension body. So effectively, you could imagine this being a cube where there are forces acting out or pulling out on this. But one of the things with this is, as we mentioned before, the area will try to contract and minimize itself. So basically, in terms of thermodynamics, which I'll cover some of the equations thereof in a moment, all areas try to be minimized. And this then applies to liquids in contact with solid surfaces as well, and explains the formation of the common droplet shape that we all know. In terms of surface and interfacial tension, this is based on the different types of interactions between the different phases. So you can have dispersive interactions, those being between fluctuating dipoles. So those are where you will have a temporary imbalance of charges in an atom or molecule. So you can think of things like, so some molecules you can have, as I said, temporary charges. So this can be just to do with slight changes, slight movement of charge. Whereas you can have polar interactions, which occur with specific molecules, those that have a permanent polar change. So things like you think of various organic molecules, or those with carbonyl groups or hydroxyl groups, or things like water that has a very weak dipole moment, very weak polar interaction with water. And with these two different types of interactions, dispersive and polar, we can then assemble a full and summation surface interface, a surface and interfacial tension. So our full surface tension is the sum of the dispersive and polar parts. And this is characteristic of a liquid specifically. Surfaces, solid surfaces, are a little different. I'll cover those in a little bit. In terms of interfacial tension, excuse me, there are different models we can apply to this, which I'll go into more detail later. Just talking about, what these are used for, what the equations look like for these. But effectively, in terms of measuring interfacial tension between two different phases, are gamma 1, 2, as the interfacial tension is higher, you can use that then to characterize surfaces. So the ratio between the interfacial tension of the liquid and the components of that liquid and how it interacts with the surface free energy of the solid gives you information about the difference in interfacial tension and surface free energy. And this is expressed in terms of contact angle, and can tell you about how attracted one phase is to the other phase. But this is all, and you need to sort of define your surfaces, what you're trying to measure, what type of surface you're trying to measure, what type of liquid you're trying to use, and you certainly need to have a bit of an idea about that. But I'll talk a little bit about that later, as I said. So now coming on to surface energy. So this is the sometimes called just surface energy, or sometimes surface free energy. This is applied to solids specifically, whereas we talk about surface tension as applied to liquids. So with that, it's the relative measurement of energy at the surface due to incomplete bonding. So we have a nice diagram here that shows what I spoke about earlier, in terms of we have more balanced and surrounding forces and interactions in a bulk material, as opposed to those unbalanced forces at the surface. So just release one more poll question. Thank you. So effectively, surface energy will be higher if the bulk interactions are stronger, or if the actual surface exposure and area is greater. And we can define this by the energy required per unit area to increase the size of the surface. We can, common units for this are millinewtons per meter, although occasionally you might see units of dynes per centimeter, which you can convert between. the dynes per centimeter is a non-SI unit, but you still see it occasionally. And quite a lot of the time, if you want to do very sort of quick and dirty measurements of surface energy, you can get dyne pens, which have inks of specific surface tension in there. But I digress and should continue on to this. So talking about the effects of surface tension on liquids. So this would cause a change of shape to minimize the interfacial area. As I said, thermodynamically, all systems want to minimize their interfacial area. So with this, what do we see? We see droplets form a spherical shape when they're not interacting directly with another solid phase. So if we have a liquid phase falling in the air like a raindrop, that will be spherical unless it's traveling at an extremely high speed. Or for emotion phases, so one liquid that is typically immiscible in immiscible in another liquid, and will eventually separate with an emulsion. This will form very small droplets. On solids, this change of shape is typically not possible. The bonds are far stronger. So the effect of surface tension on a solid would be the wetting with a separate phase, a separate liquid. And thermodynamically, we can explain that these processes will proceed spontaneously. It is thermodynamically favorable to do so. And I've sort of talked about this a little bit already, but what do all systems want to do in terms of thermodynamics? If you think, to answer the poll questions, just see the answers from the others. Yeah, I mean, please do answer the poll questions. I mean, it's good for you guys to chat. To chat here, please, feel free to interact with the other audience members, of course, everyone. And coming back to this, so all systems, they want to thermodynamically minimize their energy. Just one comment from Amit there. So the video from this will be shared to you all later. I have the slides from data physics instruments will be shared, so you will have those, and you all have the recording. And this will also be present on our website, surfaceventures.org, later for you all to see. So thank you. Coming on to this, into thermodynamics. So the what happens is, the easiest way for a system in order to minimize its energy is to minimize its area or reduce its surface. So basically, these spontaneous processes lead to the reduction of the free enthalpy, or the sort of the total energy in terms of pressure and temperature, or volume and temperature, I believe, of the system. This is exergonic. Basically, it is releases energy from the system. And this changes the free enthalpy. And of course, with this, we are doing interfacial work, as I talked about before. We can talk about this in terms of the Gibbs fundamental equation. So we'll go back. Next slide, I'll just review some of these terms, but just so you can see the equations for these. So we can have the change in Gibbs free energy, or in terms of the area, with constant temperature, pressure, and constant amount of substance. So if that is isothermal, isobaric, same temperature, same pressure, constant amount of substances, for the area to get smaller, this is exergonic, so it will proceed spontaneously. In terms of that, just talking about some of the key terms that we have here. Enthalpy is the sum of the system's internal energy and the product of its pressure and volume. So this is so temperature is changing variable there. Entropy, in terms of this, is the sum of disordered states, randomness, or uncertainty in a system. And then Gibbs free energy is the thermodynamic potential used to calculate maximum reversible work performed by the thermodynamic system at constant temperature and pressure. So with that, we can think of that in terms of the work used to either that goes on to minimize the surface area, or the work that can be put in to increase that surface area again. It's reversible. And now we come on to wetting of solids. So liquid phase in contact with a solid phase surrounded by vapor. So we model this in terms of what's called the three-phase contact line. So three tension surfaces in contact with each other. We have the solid interface, our sigma S, our solid liquid interface. We're using that gamma term there, subscript SL, and then the liquid surface sigma L. And we do this in terms of an ideal surface. It's homogeneous, it's isotropic, inelastic, chemically inert, and flat and unstructured. So basically as perfect as we can make it. And with a static situation, we have a nice equilibrium of those forces at the three-phase contact line. Excuse me. And the liquid will form a contact angle. As I talked about earlier, it's a ratio of the different tensions involved. So we can do this in terms of Young's equation. So with that, it's the surface free energy is equal to the surface tension between the solid and the liquid, plus the product of the contact angle, or the cosine of the contact angle, and the surface tension of the liquid. So that gives us a ratio between the surface energies of the phases in contact here. And then in terms of contact angles, these can be used in terms of quite a few things. So calculation of the surface tension of the liquid, knowing things about the solid surface, calculation of the surface free energy of the solid when you know the parameters of the liquid, and calculation of the work of adhesion between the two phases. And we can characterize these according to adhesion, wettability, bonding, or cleanliness. So if we have a low contact angle, we have what's called a hydrophilic surface, where the surface of love, it's water loving effectively. So it is well, there are high forces between the solid surface and the liquid, and it is very wettable. Whereas if we have a hydrophobic surface, we have a high contact angle because there effectively is less bonding between and therefore the solid and liquid are less wettable to each other. And then furthermore, on contact angles, we can talk about different types of wetting behavior and classify them such. So we have hydrophilic surfaces where we have angles of less than 90 degrees. And we can think of this in terms of cohesion and adhesion. So the cohesion is less than the adhesion in the liquid. So effectively, in terms of ratios between the surface energies, the solid has more energy in order to basically make the droplet wet to the surface. Whereas if we have something hydrophobic, where the angle is greater than 90 degrees, you have a different case where it's flipped. The adhesion is greater than the cohesion. If it is 90 degrees, we can effectively say these two are equal. And we can have super hydrophobic, where if we have the contact angle somewhere between, there's some different definitions of this, but generally between 120 and 180 degrees, the cohesion is greater than the adhesion. So this angle is a measure of the ratio between the cohesive forces perpendicular to the solid surface and the adhesive forces. So the adhesive force acts perpendicular to the solid surface. The cohesive force acts along the bisecting line of the contact angle. And then we can sort of think of this similar to if we go back a little bit to our Young's equation there, the cohesive force divided by the adhesive force is 1 minus the cosine of the contact angle. Coming on to this, we now have superhydrophilic surfaces. So we can have superhydrophobic, where we have an extremely high contact angle. We can also have an extremely low contact angle. This is where the water will spread extremely quickly. This is something that is quite obviously very desirable for dyes, paints, and varnishes, where you do want it to spread very quickly and wet on the surface. Here we go. Sorry, a little comment from Amit there. Super hydrophobic materials have a contact angle of more than 150 degrees and a roll off of less than 10 degrees. Thanks, Amit. Just in preparing for some of this, some of the literature is a little bit fuzzy about, the where hydrophobic and super hydrophobic is. So I sort of went with the widest range of angles possible, obviously, depending on where you get your, on what you look at. But yeah, 150 degrees more than, and obviously with a maximum of 180, because at that point there, it's just a droplet. It's completely non-wetted to the solid. So thanks, Amit. Coming back onto this, the opposite of that, a hydrophilic surface, show a contact angle of 0 degrees when done with conventional calculations, so measuring the contact angle, so using something like a goniometer. And this is where characterization of said surface becomes quite difficult, and where we need to move into the use of imaginary contact angle, which we'll talk about a little later. In terms of the thermodynamics of wetting, a little bit more thereof. Solids and liquids, when they come into contact, you can think of this in terms of the increase in the solid to liquid interface, and you can have different things happening with the liquid surface. So you can have that shrinking, and these are the equations that define that in terms of the work for the solid, liquid, and adhesion. So I'm not going to go through these in a lot of detail, but because the video will be available later, you'll be able to look at these. We can think of this in terms of the liquid shrinking if wetting cannot be achieved. We can have immersion, where one phase is immersed in the other, and then spreading. So we can make predictions about this if we know what the surface and interfacial tensions are. We're able to, as I talked about before, we're able to define certain things about the interface and about the different phases. So now I've just want to take a couple of minutes here to just sort of say thank you all for answering the poll questions. But I was also curious about in what context you've used surface tension and surface energy, and how you measured it. What methodologies you used. I think there's a little bit there was a question there about that. So between surface tension and what's the relation between surface tension and density? So Sebastian, if you have any input here, that would be very helpful. This question, but about the relation between surface tension and density.
Yes, so thank you very much. So I think there is typically not a direct relation, because you can think about the following example. You have water, completely pure water. It will give you a surface tension of 72. Then you add a little bit, just a trace of a surface active molecule like a soap inside, and all of a sudden you have a very low surface tension in the 30s or something. So there cannot be a direct relation. But maybe what you are referring to is that some metals with a very high density, like mercury, for example, or some gallium alloys, they have very, very high surface tensions typically, and also at the same time, also high density, but this is not a typical relation.
Thank you. Okay, so I'm going to move on momentarily, but just it would be great for those of you that have worked with surface tension and surface energy, if you could, if you don't mind sharing in the chat, in what context you were doing these measurements. It would just be quite interesting for us to know, as this is slightly different from some of the workshops that we've ran before. So just a bit more information. There's something from Benedict there, defining the properties of a novel material, taking dynamic contact angles with a range of liquids. Thanks. It's very, very interesting to know. Okay, so since I just talked about super hydrophilic materials, I'd like to talk about some of the different models here. And begin with the Zisman model, specifically to talk about the case of critical surface tension and critical surface energy. So the Zisman model was published in 1964, and it assumes that the surface energy of the solid is equal to the maximum surface tension of a liquid that can give, a contact angle of 0 degrees. This is critical surface tension. So using a range of liquids with different surface tensions, you're able to measure a range of different angles and cosine thereof of those angles until you reach a point where you get a critical surface energy where for that specific liquid, or for the maximum for the liquid with the lowest surface tension, so you're maximizing the use of the surface free energy of the solid, you get an angle of 0 or a cosine of 1. But obviously with this, your surface could still have a higher surface energy than what you are able to measure with your set of liquids. So if we think about, going left of that critical surface tension, there's still an area that can be explored here as we go into imaginary contact angle. So this is something Sebastian's going to talk about a bit more in terms of tensiometry. But now coming back to the Zisman model, it ignores the impact of polar interactions and is only accurate for non-polar surfaces, something such as polyethylene. Whereas for polar surfaces, a different model has to be used. So for this, we can use the Folks model, also published in 1964. So this assesses the interaction between liquids and solids in terms of dispersive, sort of van der Waals, or temporary dipoles, and our polar interactions. So we can split the surface energy into these different components. And without going into the full maths of this, we can assemble this our primary Folks equation there. And you can use multiple liquids here with different polar components. So this is where you can selectively eliminate different parts of this equation in order to perform your full characterization. So you can do diodomethane, which has no polar component, and then water, which is polar. Another model that we can reuse is the OWRK, published in different parts in 1969, 1970. It is mathematically equivalent to the Folks, but it's derived from slightly different principles. We have the equation there. This requires at least 2 liquids with known dispersive and polar interactions. If you don't know this, you can determine this with a reference solid, such as PTFE. But commonly we'd use, and I think data physics would commonly recommend 3 liquids, so diodomethane, ethylene glycol, and thiodeglycol. And then you can use this for similar materials to the Folks, but it fits better for lower surface energy surfaces. But considering all of the different, the amount of 3 liquids, it requires more experimental work than the Folks model. One other model here is the Van Osgood model, where we're considering something slightly different again. So most surfaces, or many surfaces, can be considered in terms of their dispersive and polar interactions, as I talked about previously. But a lot of surfaces can be considered in terms of hydrogen bonds, which aren't considered in terms of the Folks or OWRK. Apologies, the spell check must have decided I was trying to spell work there. Van Osgood was published in 1992 and instead considers acid-base interactions, or hydrogen bonds. So that is the equation that defines it there. And by choosing a liquid with a purely dispersive component, such as cyclohexane, you can then reduce the equation to what you see below. So where you're just considering dispersive parts, and you can then use this as opposed to the other models that I've talked about. But coming on, to here where we can talk about when do we actually use these different models. So for, as I just said, non-polar surfaces with low surface energies, Zisman is recommended. For moderately polar surfaces, folks. For higher surface energies, better for higher surface energies, however, or OWRK. For polar surfaces, such as inorganic, organometallic, and ionic surfaces, Van Osgood. And then if you want to determine the polar and dispersive interactions of liquids, having a known reference surface and using either Folks or OWRK. In our final few minutes before we sort of open up the Q&A, again, if you do have any questions about this, please type them in the chat. Talking a little bit about the effect of surface texturing. So this, as I said, most of these measurements we would like to do with an ideal surface, a nice flat surface. However, this is not representative of any actual surface you are going to measure. If you can minimize your surface roughness, you can essentially deal with that ideal surface. But quite often, we're dealing with specifically textured surfaces or ones that are specifically rough. And with this, we need to think about time and time dependence in the wetting process, in the filling of the asperities, or the actual, the little bumps or sort of valleys on the surface. We can model this in a few different states. There's the first of which is Cassie-Baxter, in which we assume that the asperities are filled with air and our droplet is sitting on top of this textured surface. There's the Wenzel state, where the asperities below the droplet are filled with water. So obviously you can see that our sort of contact angle there is taken from a slightly different point than Cassie-Baxter. And then differently, then we have our ideal surface, or where we can think about our classical complete wetting, where the droplet has disappeared into the asperities, and we can look at this like our ideal surface. I've talked about surface energy of different surfaces, but that's not to say that a surface, it has a fixed surface energy, and this cannot be changed. So this is something Sebastian will talk about as well in the demonstration. But there are a few different things that you can do to modify surface energy. And that's not to say that all high surface energy materials will maintain that high surface energy when exposed to atmospheric conditions or in different conditions. Contaminants will absorb onto the surface, such as oxidation of metals is a classic one. So we can perform different surface treatments to raise the surface energy by removing contaminants or forming high surface energy functional groups. So we can either use UV ozone treatment or plasma or corona treatment in order to modify the surface in order to increase its surface energy. And then coming on to a little bit about how we determine surface and interfacial tensions and energies for liquids. The deformation of said liquid is a result of the acting forces. So we can use contour analysis or contact with a solid. So that's where we can use a contact angle goniometer. We can either model the contour of a droplet or its interaction with a surface, or for the solid, where it doesn't deform, it will instead manipulate a liquid in contact with its surface. So with various test liquids, we can perform a more indirect investigation. So this is coming a little bit more onto the experimental methodologies that you can use for this. In terms of acting forces, we can use tensiometry, which directly measures the forces, or we can use things like where the shape will change. We can use contour analysis, which is and then an optical method. In terms of tensiometry, this is using the principle of deformation of the liquid surface interface upon wetting. There's a couple of different ways to do this, such as the Wilhelmy plate at the top or the Denoy ring at the bottom on the right-hand side. So from this, we can get out the surface tension of the liquid, the interfacial tension between two liquids, dynamic contact angle of liquids on solid substrates and fibers, dynamic contact angle on powders, slightly different method, the Washburn method, and the surface free energy of solids, fibers, and powders. A little bit about contour analysis. So this is where we have our needle that's dispensing the droplet. We do an ideal fit to that droplet, from which we can calculate the surface tension of the liquid. This is the pendant drop. The interfacial tension between two liquids. We can do a liquid drop in a second liquid. The contact angle of liquids on solid surfaces. So this is where we do a sessile drop. So put a droplet on the surface that is stationary, and then you can measure that. You can do captured drop or bubble. And then again, surface free energy of the solids we can do by sessile drop. You can also do static and dynamic contact angles. So static angle, contact after completion of the wetting process, whereas dynamic, you are allowing it to both wet and de-wet the surface. So needle and drop method you can use for this form of contour analysis. Tilting base, so we can do, we see changing the angle there, which is again contour analysis, or the Wilhelmy plate. A comment there from Yangxi on, apologies if I mispronounce, I'm terrible with name pronunciation, saying they did a few studies, the wetting behavior of a lotus leaf a few years ago. Professor Cheng, thank you. That would be a good resource for everyone to take a look at. Is the lotus leaf super hydrophobic? Thank you for that. Coming on to, as I finish up my presentation, the applications of wettability analysis. So this is key in materials analysis. Some of you have talked about different types of materials analysis that you are, excuse me, that you are undertaking. So for things like textiles, self-cleaning glass, anti-fogging and anti-icing glass, biomimetic materials and biomaterials. Apologies for the slight error there. Tensiometric. And yes, descending, not rescending. Apologies for that. But sorry, coming back onto these slides. Other applications for solar panels, obviously these are exposed to the atmosphere and rain, where anything on the so we'll come to that question in a moment. Thank you, Mojtaba, for that. Solar panels are exposed to rain, and obviously anything on the solar panels will affect their function. Biosensors, atmospheric water collection and harvesting, chemical shielding, corrosion control for electrochemical or general corrosion. A liquid in contact with the surface. If you can't wet a liquid to a surface, very little corrosion will occur. So that is very important. Biological adhesion and biochemical cells and battery materials and hygroscopic materials. We specifically design a material to uptake water and absorb water. So that is the final part of my presentation. I would just like to sort of make you all aware that our next Surface Ventures webinar will be 1 week from now on the 20th of January at 11 a.m. Greenwich Mean Time on the mechanical characterization of supersoft hydrogels with Dr. Dichu Zhu at the University of Southampton. I will put up the registration link for this a little later. For now, I'd like to come on to ask any questions. We have one there from Mojtaba on what is the benefit of measuring dynamic contact angle.
Okay, Sam, if it's okay for you, I would help to answer this question.
Please go ahead.
Perfect. Thank you very much. So dynamic contact angles, in some cases, we need to measure them because you are not able to measure static contact angles. This is, for example, the case when you want to measure on very fine powders. So the Washburn method, this is a dynamic method to measure contact angles. Also, typically on fibers, we are doing dynamic contact angle measurements and not static contact angle measurements, just because a tensiometer is able to do dynamic contact angle measurements, and the optical contour analysis system, this is able to do both. But in order to use optical contour analysis, of course, our substrate needs to be big enough that with a conventional optic we can see the drop. And if you imagine a powder, very, very tiny particles, or fibers, tiny fibers, you cannot place a drop properly on this and then wait until it's in an equilibrium on the surface, because it will evaporate very, very fast and it is just too small to detect it properly. So in these cases, for fibers and powders, typically dynamic contact angle measurements are done using a force tensiometer. Then, in addition, if you have a solid extended surface and you have the choice to either do a static contact angle or a dynamic contact angle with an optical contour analysis method, often people choose the dynamic way, because dynamic contact angle measurements, there you get an advancing contact angle and a receding contact angle, and the difference between these two is called the so-called contact angle hysteresis. And this is teaching you something about the absorption of your droplet. How strong is it adhering to the surface? So this hysteresis value that you can only get from dynamic contact angle measurements, these are important for absorption studies, basically, and adhesion studies.
Okay, thanks, Sebastian. I have a question here. Comment on the excuse me, sorry. Comment on the surface characteristics for both corrosion resistance and biological adhesion. This is a very broad thing, but in short, for general corrosion or electrochemical corrosion, it is the chemical interactions between two different phases that's causing essentially the chemical change in a material that you don't want to occur. That is effectively corrosion. That's causing a loss of material. For most corrosion, for pretty much all corrosion that is generally considered, it's the contact with water, or with seawater for say metals. Obviously, if the water can wet to the metal, there is an interaction going on between the metal and the water, and this will eventually lead to corrosion. Whereas if you can create, or if you can modify a surface such that it is more hydrophobic, this will slow down the corrosion. In terms of biological adhesion, so this is quite often in terms of biological adhesion, this is where you're dealing with surfaces that are textured in such a way, or have specific surface chemistries in order to aid adhesion. It's pretty broad. I mean, Sebastian, if you have any comment on any of these things, but that's sort of...
Yes. Maybe I very quickly jump in for the biological adhesion. Later on, we are talking about the tooth implant. And for the tooth implant is also the goal that the surface is engineered in a way so that cells can adhere very well on this. So probably we can elaborate a little bit more on this when we show you this measurement on the implants. Then you have a practical example.
Great, thank you. Question from Jean about the surface texturing, apologies, and considering a non-flat idealized surface, do you have an idea about the order of magnitude of the roughness of the surface in either micrometers or nanometers that begins to affect the contact angle measurement? Thank you.
I would also comment on this quickly. So this depends on how big you choose the drop that you use for your measurements. Typical measurements are done with drops in the microliter range, and a microliter drop, this has typically a diameter in the millimeter range. But there are also systems available that can make tiny droplets in the picoliter range, and these picoliter drops, they have then a diameter in the micrometer range. So this means if you have a microstructure on the surface and it's micrometer range, then you can still get a smooth and flat area where you place this kind of tiny droplets on. And in this case, you are measuring the real contact angle. However, if the size of the drop is significantly bigger than the structure that you're having on the surface, then you are not able anymore to measure the real contact angle. So then you are measuring the so-called apparent contact angle. So you look at the substrate from the side, you see a smooth surface, and the system can then only give you the contact angle towards the smooth surface and not towards the microstructure. And in this case, it makes sense that you use a device, a surface profile analyzer, for example, and then you determine the roughness of the surface. Then there are different roughness parameters. So one of them is called SDR. So this is a two-dimensional roughness parameter. And this roughness parameter can then be used to correct the contact angle. Okay? But very important, size matters. So you should always, if you want to study a process, for example, a printing process where you know, okay, the printing inkjet ink drops, they are in the picoliter range, then you should also do your measurement with droplets in the picoliter range to avoid trouble. Because if you print on paper, you know, paper also has a microstructure on the surface. And if you then want to predict the wettability during the printing process, it makes sense for the ink optimization to also do the measurements with picoliter droplets.
Yep. Another question here. Do we need at least one more technique like ellipsiometry or atomic force microscopy to complement the info? A little comment on AFM. If that's in terms of visualizing or measuring the structure, then sure. One thing also to be aware of in terms of AFM, if you're doing surface roughness measurements, is that, you know, be aware of the size of the AFM probe that you're using, because, you know, if that is relative to the actual size of the droplet that you are then using, whether you're doing, you know, your sort of more typical microliter or your smaller picoliter measurements. Yeah, so again, sort of coming back to that in terms of size. Any comment on ellipsiometry, Sebastian?
So what I think this question is probably aiming at, what is completely defining a surface? And in this case, I have to say, well, the surface chemistry is one element. So with tensiometry and optical contour analysis, we determine surface chemical properties, but always the surface morphology is also important to fully characterize the surface. So this means, of course, atomic force microscopy, this information is additionally valuable to completely characterize your surface.
Yeah. And also just to be aware, again, if you're, depending on the size of the size of the analysis you're doing, you could apply other surface roughness or surface texturing analysis techniques, such as white light interferometry or simple, you know, larger scale stylus profilometry, depending on your surface. But AFM is always a good shout. Question here: does higher contact angle always mean lower adhesion or wettability? Sebastian, would you like to?
Yes, I would like to comment on this. So in general, I think it is correct that higher contact angle, this means that the wettability is lower. But for the adhesion, it's a little bit more complex, because you have seen from Sam's slide, so there is the Cassie-Baxter state and there is the Wenzel state. In the Wenzel state, the surface is wetted completely, even the pores is wetted. And this means you have a big contact area, so this means you have a high adhesion. Now you could have a drop on the exactly same area, but you do not wet the cavities, only you wet basically the mountain tops. So then there is a smaller contact area, and then of course also a smaller adhesion. So for the adhesion, not only the contact angle is important, also it is important what kind of surface morphology you're having. So compare this, we call it the rose petal effect. So you have a rose leaf, the drops on the rose leaf, they have big contact angles, and the adhesion is quite high. In fact, the drops stick there. And then you have the lotus leaf, where you also have big contact angles, but there the drops, they roll off so easily. So this is a different in adhesion, even so the wettability looks comparable.
Yeah. Thank you. So there's 3 more questions. So we'll take these and then we'll proceed on to the demo. So we've got one question here, similar question with Gene. We deal with a solid surface. Most samples have, I presume that's a significant roughness. Wenzel or Cassie-Baxter needs some geometric parameters of the surface. How do we evaluate the surface energy of the surface without knowing it? I presume that's without knowing the roughness.
So I quickly also comment on this.
Mm-hmm.
So what I would do in an ideal case, you know the roughness of the surface, and then you can correct your contact angles from the measured contact angles, the apparent contact angles, to the real contact angles, and you use then this corrected contact angles for the surface free energy analysis.
Yeah.
So if you do not have these roughness parameters, then of course you can still do a surface free energy analysis, but then you have to be aware that based on how strong the roughness of your surface is, the surface free energy, it will not be correct.
Yeah. Thanks, Sebastian. We got one here about asking about what parameters are measured by the tensiometer.
Yep, so this I would also comment on. I later on also show you this quickly. So what we can measure is we are only measuring a force and we are measuring the time.
Yeah.
And from this force and time measurement, the device can calculate multiple things. It can calculate the surface tension, interface tension, dynamic contact angles, for example. It can calculate adhesive forces, but the basic parameters we are measuring, this is only time, weight, and the temperature.
Yep. So just to further comment on that, we have the data sheet for the tensiometer that I will be releasing, and some further application notes on relevant to the demonstration using the tensiometer. And then there are 2 other ones on optical contact analysis, which are related to this, but just to make you aware of those with DCAT are related to the tensiometer. When I release those later, and the OCA ones are optical contact analysis. So final question, Wilhelmy plate is better or Denoy ring method? How much better and why?
Okay, I think I also very quickly comment on this one. The Wilhelmy plate method has an advantage that you do not need to know the density of the liquid that you are studying with the Wilhelmy plate method. So this is a big advantage. But typically the lamella at a Wilhelmy plate is smaller than the lamella and also less weight than a lamella at a Dunois ring. So this means if you measure an interface tension where the densities of the upper phase and the lower phase are very similar, you can have pretty small masses of the lamella. And in this case, it's of course better if the lamella is bigger. So for Dunois ring with typical sizes, the weight of the lamella is 3 times higher than for the Wilhelmy plate. So this gives you an advantage when measuring interface tensions. However, for Dunois ring measurements, you need to know the density of the liquids that are involved in this measurement. So saying which one is better is a bit difficult, but I can at least say, okay, for fast measurements, if you don't not know the density, Wilhelmy plate is better, and I would choose for interface tension measurements always the Dunois ring method.
Okay, brilliant, thank you. So I will stop sharing my slides for now to let you switch over and begin the demonstration.
Perfect. Good. I hope you can already see me. Also, warm welcome from my side, and thank you very much to you, Sam, for introducing all this concept so well. So I think this we can now very well build on. What I would like to do with you now first is I want to also show with you a couple of slides. And based on these slides, then afterwards, we are going and we show you how this kind of force tensiometer is indeed working. So let me first share with you our slides here. So today we talk about measuring imaginary contact angles on hyperhydrophilic surfaces. First of all, what device are we using? We are using a force tensiometer. And since we call it a demo, you can see here in the background directly next to me, I have the tensiometer. And during my presentation, I will sometimes come over here and show you a couple of steps and also explain you what is going on the slides. So we have here a little bit of a mixed thing, and I go back and forth from the screen here to the measurement device to explain to you how it works. But before I do this, I want to very quickly introduce our team here. So we are Data Physics Instruments, and we are a manufacturer for devices that you can use for characterizing surfaces and interfaces. We are based in Germany, and at the moment we have around 40 employees. And I think from the polls that you showed, I saw that many of you are working in the research and development field. So also in our team, around 1/3 of the people, they are working in our development department because, you know, doing this kind of devices is really development intense. We are in the market now since 25 years, and below you can see our portfolio. So we have shown you just now, there are optical contour analysis systems on the very left side. There are force tensiometers here in the second position. And in addition to this, we are making spinning drop tensiometers for measuring very, very low interface tensions. We are making dispersion stability analysis systems. We are making setup potential analyzers, humidifiers, and also surface profile analyzers. But today we focus on the two devices on the left side, and mainly we will talk about the force tensiometry. Good. How does a tensiometer look like? So you see it here. This one is our DCAT25. And I guess all of you know a classical tensiometer. This was a device in order to characterize liquids regarding their surface tension and interface tension. But modern tensiometers, they are in fact much more powerful. So they can measure automatically critical micelle concentration. They can do adhesive force measurements. And what we will show you today, they can measure dynamic wettabilities and dynamic contact angles on different substrates. So the substrates, they can be powders, they can be fibers, or they can be the implants that I want to show you today. So this means a tensiometer is a device not only to characterize liquids, but also solid substrates. And again, I thought this poll that we did today, this was super, super interesting because, you know, I think more than 30 people, they already worked with the optical contour analysis system, but not even a handful, when I checked, were working with the force tensiometer. So this was quite surprising to me. So I'd explain to you something new today, I hope, and open your eyes a little bit that this classical force-based method is still very, very powerful. Good. How does the tensiometer work now? Let me quickly go over to our device here. So what we are having is, we are having here the head of our device, and inside the head of the device is a very, very precise balance. You can see here below this piece here, this metal piece, this can connect a sample, a probe, to the balance that is up in here. Now, let me show you how this is working. I have now here in my hand a so-called Wilhelmi plate. So this is a plate made from a platinum iridium alloy. And this is our probe that we are using to study surface tensions, for example, of a liquid. So the system is working quite simple. So you just slide this plate up here. I turn it in your direction that you see it well. And now the device is ready to do the measurement. Okay? This Wilhelmi plate now is connected to a balance. And in fact, this is a super precise balance that you have to do using for this kind of measurements. And you see at the moment when I touch it, nothing is happening. So the reason is this kind of device, it has a so-called automatic clamping and crash protection. You saw with the touchpad, I have opened this device now. And when I touch it now, you can see the Wilhelmi plate is swinging. So now it is actually measuring the weight that is attached here to the balance. Then you see I have here a sample vial, and in this sample vial I am having now water. You have here a thermostat jacket to very well control the temperature of the water, and you have down here in the lower part of the device an automatic sample stage. So this sample stage then during the measurement, it is moving up and down automatically controlled by the software. And like this, you are submerging the plate into the liquid, and then the balance is recording the weight of the lamella, of the water lamella that has attached to the plate. So I show you this quickly again here on my screen. Let us have a very short look. So again, as mentioned, we are having a balance in the top of the device, and then we are connecting a probe to this balance. And what we are doing is we are registering the weight. Okay, and the weight that we are registering is of this lamella here. Now comes an interesting thing. When you have a look here at the weight of the lamella, you can see, okay, there is a force involved, the tensile force, and this tensile force you see here is regarding the contact angle. And this is now interesting. Now you have to imagine, I can only measure this force here. Vertical force. I'm not able to measure this kind of tensile force. because I do not know the contact angle theta. In the other way around, this means if I do not use a known solid probe, but I check on a known liquid, then maybe I have a chance to determine this kind of contact angle. And this is the concept that I want to teach you today and show you how it's working. So maybe this is a little hint for you. So you have seen my device here. I did not install the windows around because I want to be able to move here freely and show you the device. But from the pictures here, you see that typically there is a glass housing in order to shield this very, very sensitive measurement from air conditioning blowing onto it or some other environmental effects. Good. What can the system do? Well, the system can, of course, measure at room temperature, but some people, they want to measure the molten polymers. Then you can have the possibility to adjust temperature chambers. You can also adjust here automatic dosing units. So this is a very versatile and modular system with a lot of different accessories that you can still use in combination with it. I want to now also give you a very short comparison. So you have seen from the poll, most of you people have used optical contour analysis systems on the right side here. And optical contour analysis system, I think this is the more modern technology because, you know, in order to do this, you needed to have good enough computers to automatically evaluate the shape of a drop. So these methods here, computer assisted, they came up at the end of the 90s, basically, to be widely available as commercial units. These devices have some advantages because you only need very, very tiny sample volumes in these little syringes that you see in here. And when you have a sample, like my telephone here, for example, this is not a homogeneous sample. You know, here the wettability will be different than on the glass lens. So with the optical device, it's very easy. You place the syringe here, then you get the contact angle on the lens, or you do it here, or do it here, and then you will be able to locally assess the wettability of the surface. If I do it by tensiometer, I would have to cut down my phone to pieces, so I cannot directly measure here with a tensiometer because it's not possible to dip the complete thing into the liquid. So this means optical tensiometry has the advantage that we can locally measure on individual areas of the sample. We are using very little sample amounts, and it's a fast process, in fact. But so why are we still using force tensiometry? This is a more classical method, in fact, but it has some very, very significant advantages because when you are dealing with tiny surface areas, then you have no chance to place a single drop on there and observe it by a video camera system. So when you are dealing with powders, for example, individual fibers, or strongly absorbing material, then you should always go for the force tensiometer to study the wettability. But, and this is now very important, the surface tension and the force tensiometer, it can be a very powerful device if you have extremely hydrophilic surfaces. The reason is, just imagine I have a very, very hydrophilic surface. I place a drop of liquid on it. What does the drop do? It just spreads completely over the surface. And then I get a contact angle of 0. But what if I want to still improve the wettability of the surface? Because you have seen from before, wettability is an important characteristics on how well cells are adhering to this material. How well a new bone replacement material gets accepted. This depends on this, how strong the cells adhere. So there must be a way that we can use in order to still quantify differences between very, very hydrophilic surfaces. It cannot be that we just place a drop of water on it, it spreads completely, and then we say, oh, well, this thing is very, very wettable, contact angle is 0. Like this, we are using a lot of potential to optimize this kind of materials further. And this is the concept that I want to show you in a moment, the concept of the imaginary contact angles. But before, I have to give you a little bit more background information. Classics is, with a force tensiometer, you use Wilhelmy plates or you use Dunois rings, and you characterize the surface tension of the liquid. Very, very straightforward, very easy measurements. But the device is so much more powerful because you can use the device then also to detect the dynamic contact angle on solid substrates like this kind of tooth implants. This is an indirect measurement. So I rely on that the water that I use for testing, it must be really, really pure, because I'm just saying the surface tension of this water is 72. And based on this surface tension value of 72 millinewtons per meter, the system is then calculating backwards and is giving you the dynamic contact angles. So this means for us, if we want to use dynamic contact angle measurements by a force tensiometer in order to characterize implants, we need to first make sure that the water that we are using is pure and clean. Because we do indirect measurements, we then use this water in order to assess the wettability on the implant.
Apologies, Sebastian, just before you move on. So I had a question there from Marina asking about basically saying tensiometer is used to analyze liquids and not solids. So I'd just like to highlight what you'd said there. It's effectively to say, depending on what you know about the liquids and solids that you're measuring, depends on, and also, what you want to measure. So,
So let me put this like this so that it's clear for everyone. If I put a known solid into my tensiometer here and I lower it into a liquid and pull it out, then I can learn something about the liquid. But I can also do it the other way around. I can use a known liquid, like water, for example. Then I dip in an unknown solid surface, and then I can learn something about the solid surface. Okay? So this is vice versa possible. And I will explain this later on with my example here of the tooth implant, how this kind of measurements need to be performed so that you get reliable results. But maybe before we go into this, again, I want to show you how does a dynamic contact angle measurement with a tensiometer work. So, what we are doing first is we have our water, we have our sample, and the sample is lowered into the water and then pulled out again. And when we push the sample into the water, we are getting here this inverse lamella. And this angle here is then a so-called advancing contact angle. When we afterwards pull out the sample, then we are getting the receding contact angle. So you always get two, an advancing contact angle and a receding contact angle. And the difference between them is the so-called contact angle hysteresis, which is teaching you something about the adhesion of the liquid on this material. So the bigger the hysteresis, the higher is typically also the adhesion. Now let us go a little bit into the details of the measurement. So the equation we are using is this one here. So the cosine of the contact angle must be equal to the mass of the lamella that we are detecting, gravitational constant divided by the wetted length. So the wetted length for my phone, for example, would be, if I dip it into water, it would be 2 times this length and 2 times the thickness added up. So this is the wetted length. This is how long is the lamella around my phone. And then you can now see here, there is also the surface tension inside. So this means for us, if I know the surface tension of my liquid, it's a known liquid, it's water, it must be around 72. If I know the wetted length of my substrate, it's easy, I can measure it. And then if I have a device that can very precisely determine the mass of the lamella for me, then all terms here on the right sides, they can be measured or they are constants and they are known. And this means, okay, I can take this equation here and then very, very easily calculate the contact angle. Now there is one point you see here. We are taking the mass at height is equal to 0. So this means I do not take the mass of the lamella when the thing is already deeply in, because then I have some buoyancy effect from the platinum iridium plate or from my material that is underwater. So I need to make sure, okay, I take the value when the tip of my sample is just touching the water surface, not underwater, because then you have a buoyancy effect. So how do we do this? Measurement is very, very simple. We take water, we make sure it's pure, and then automatically the tensiometer lowers our sample into it and pulls it out again. And from this, we get this kind of graph here on the lower left side. So you have on the x-axis the immersion depth. So how deep is the thing inside the liquid? Then on the y-axis, you have the weight of the lamella. So this means our sample is dipped in, okay? So you can see when dipping it in, the mass is going down. And what is the reason for this? This is the buoyancy effect, of course, of the water, that you push it down, that is also playing into effect here. Then you pull out a lamella from this. And then you see here, only thing our software does, it's interpolating this to line, extrapolating, and it is making the intersection here with the y-axis. And then you are getting the mass in and mass out at the height 0. And then this is put in the equation here, and then you get your cosine of theta. Good, but now we have a very, very big challenge, because you can imagine the weight of the lamella here. It can be quite high if you have a very, very hydrophilic material where the water easily crawls up. Then it can be that the term here on the right side here, it can be bigger than 1. But you know, the cosine, it's defined in a way that it cannot be bigger than 1 if you are using normal numbers. So this would mean whenever you have a very high mass of the lamella, you would always get the result 0 from this equation if you work only with real numbers. And now here comes in the imaginary contact angle. So what we are doing is we are now just defining, okay, theta, this contact angle, it can be a complex number. So it's A plus BI. And A, this is the normal contact angle, classical contact angle that you see here on the scale. B, this is now the so-called virtual or imaginary contact angle. And when you now have a little look on the right side here, in red, this would be a classical contact angle measurement, okay? So you go up to here, and then you see here, now I have gotten a virtual contact angle of 0. And then for all other immersion depths and weights, so the mass trace, you see it's going further, 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 much, much higher masses of the lamella are possible. But the solution of this equation does not allow it. So all of the values here, they are just 0. So this means you cannot quantify whether this thing now is more hydrophilic than the comparison sample. So you have to write for 10 samples, oh, okay, contact angle is 0, I'm sorry, now my experiment is done. I don't know which of my coatings or which of my surface engineering was the most successful to make it even more hydrophilic. So let me go one graph further here. So if we now go and we also allow complex numbers, then you can see, okay, now the virtual contact angle, it is just giving you here an imaginary result. So here you just have from I0 to I30 or even higher, just an additional scale on top of it. So this means the higher the imaginary contact angle, the more wettable is our substrate surface, okay? So the end is not at 0. This is the important message for you. Now we want to go over and we want to show you this also a little bit practically. And we have tried to think about what kind of substrate and sample can we use to prove to you that this kind of imaginary contact angle measurement is useful. Then we have been thinking, okay, if you think about implant materials, no matter whether it's for tooth or for bones, typically they need to be super hydrophilic, because the more hydrophilic a surface is, the more easy it is for cells to adhere to the surface. And this helps, of course, then the bone regeneration when the implant is planted into your mouth, for example. So this means we want to check with you now how hydrophilic are certain implants. And this we do by our DCAT25, and we use the principle of imaginary contact angles. And if we have enough time today, we do 2 measurements. So first we measure on a normal implant, not treated, and then we take the same implants and we do a plasma treatment of the surface. You know, this plasma treatments, this is normally making the surfaces even more polar by introducing hydroxy groups on the metallic surface or other polar groups, basically. So what we are doing now is we start now with the experimental part. But at the very first, we have to make sure that our water is clean, because I show you this. All of this equation here and our results are only correct if the surface tension of my testing liquid is as it is in the literature. You know, the software is working with a value of around 72 for pure water. So now what we have to do first, before we do measure our implant, step 1 needs to be done. We do a Wilhelmi plate measurement and we check whether our water is clean. So we should end up around 72. And this we do on our device. And I want to zoom in a little bit for you that you can see more clearly what is happening. So you see, I have here prepared already a little sample with water inside. I have also heated up my Wilhelmi plate. So both of them are now ready for doing the measurement. Very, very important for you, when you take water for doing your analysis, this should be fresh tap water. So never use water that was stored in a plastic bottle, because the softener from the plastic bottle is going into the water and is lowering the surface tension of it. So before I start the experiment, you can see I have now opened the clamping. So now the device is active. And now I can use my touchpad and I can raise the sample vial a little bit up. So now we go over to the computer and then we run the software and start our measurement. I just very, very briefly want to show you how to do this. So I share my screen here. This is the interface that we are using to control the tensiometer. And we want to do a Wilhelmi plate measurement. And all the information in here is okay. So we just click on it and then the measurement is starting. Okay, this is for saving dialogue. And then the software, this has something very helpful for you at the beginning. So it is showing you here how this kind of measurement is done. So step by step, it's basically guiding you through the experiment so that you know what to do. What I want to show you before I start the experiment, this is here our Wilhelmi blade. And this blade is made from platinum iridium. It's a very sensitive device. What we typically do is after each measurement, we wash this blade with water and a bit of acetone, and then we heat it up with a Bunsen burner. Because you notice platinum iridium, this is a very powerful catalyst in organic chemistry. So when you heat platinum iridium up, every organic residue in the surface, it will be decomposed. And this is very important because if you have still some surfactant on the surface and you heat this blade up, it will burn off and then you have a clean and neat surface again. Okay, good. Then let me get back here to my software and quickly set up this measurement. So as I have mentioned, there is this kind of guided system that is going to show you what you need to do in the first couple of experiments. And now we can have a look at it. So let me share my screen here quickly again. So it's making sure, okay, you have placed the sample inside, you have shut the doors, I have removed mine. And then finally, it is telling you, okay, bring the sample in close proximity to the surface. And now the measurement is starting. And now I want to overlay with you what is happening here. So you see now automatically the stage is moving upwards. And in a moment, you will now see that a lamella is jumping towards the blade when it's touching the water. Yep. So you see this? Now I have set up in the software that the blade should be immersed by 3 millimeters, and now it's pulled out again. And now we go over here to our software, and you see now here, this is our result that we are getting. So we are pretty close at the 72. So we are having here 71.98. And now you can see the device is automatically now lowering the sample table. And now I'm able to take out my probe. Very, very important. Have a look at this one here. The SFT here is now 71.98. So this means this is very nice and clean water. We can use this for our next measurement step. So what we have done now is we have now made sure, okay, what is in here is really pure water and it can be used in the next step to characterize our tooth implants. Now I can remove the sample here this has done its job for today. And now we are taking the tooth implant. And for fixing the tooth implant, we have developed here a special probe holder. So this is a tooth implant. This is what is screwed into the bone of your mouth. This is what needs to be accepted very well by your body. This kind of implants, it always also have a hole on the top where you can fix a screw inside. So this is where your tooth later on will be screwed into it. And we use these screw holes now to fix a little rod inside. And then with this rod, we can attach it to our tensiometer. What I want to show you first is I use here now a little extension so that it becomes a bit longer and goes deeper down. But now we have our final setup. So now we have the tooth implant here. It is mounted inside our device. And now we can start the measurement. I just need to lower my implant a bit. I push it up too much, but like this now it's okay. So now
Either muted yourself or done something with your microphone. Apologies for the interruption, but
hello, do you hear me again?
yes, back. There you go.
Perfect. I'm sorry, guys. This was the batteries, but I'm lightning fast and have no new batteries.
Right.
Good.
We have just so you're aware, we have quite a few questions, but I'll let you continue with your demo, just so you know you have some questions on some of this once you're all finished.
Don't worry. I speed it up. Okay, so what we need to do now is we need to type in the geometry of our tooth implant. And you have seen this tooth implant, it has a little bit of conical shape, but we want to measure the wettability on the relatively linear part of it. And for the implant that I have used now, I have here the box for it. So I just show you because probably this you have also never seen how this looks like. So you know, implants, they come in this kind of boxes, and the implant is stored in this kind of cylinder. Then you have a piece on top, and then in here is a little screw that is then used to fix the implants. And this whole thing comes in this kind of screw vials here. Now we have put in the implant, and we can read here on the package. So this implant, it has a diameter of 5.5 millimeters. So I have already typed it here into the software. So this diameter is used to then calculate the wetted length. And what we are doing now is we are now starting this experiment. And again, I want to first show you how the measurement is done. So you see the implant, it is fairly high over the water level. And now the sample stage is moving upwards, and the clamping was just now opened. Okay. So sample stage is moving upwards. And what we are doing now is the implant, it will be immersed 8 millimeters into the water and then pulled out again. Okay. So probably if you look very closely, you see that the water level, the lamella, it is moving up much, much faster than the implant itself. Yeah? So you see how it's going through the screw turns. So I have later a little video that I will show you that it's a bit more clear. And now you see the effect from the buoyancy. So the implant is lowered down. So this would mean the weight, it should be dropping down very fast, but because water is crawling up the implants, this is compensating for it partially. And now we are already pulling out the implant again. Very good. We give it a little bit more, and then I want to show you here. You can see now the graph is live forming up. So now we are pulling out the implant, and then of course the mass is higher than at the beginning because we have a significant lamella now attached. And now you see, okay, we have break off and the implant is taken out of the water completely. Good. This was the first step of the measurement that we have done, and now we would do together the result evaluation. So for this, to explain to you a little bit, you have seen the implant is a bit conical. So this means the very upper part here and the part at the beginning, we will not take into account. So when we are doing our calculation now, what we are doing is, this one we don't need to remove. So we are taking our trigger lines and we are blinding out what is happening here at the beginning, because this is where the implant is not straight. So this is where it's conical. And also the lowest part we take out a little bit, and now we do our calculation. And what you see now is, you see, okay, here in the first column, we are having a contact angle of 0, both for the advancing and for the receding. So this means this is a hydrophilic implant. But the interesting thing now is, you see here, we are getting an imaginary contact angle. So in this case of around 110 degrees. And this is now the interesting point. If you would have analyzed this implant with a classical method, only using real values for the contact angle, then you get a contact angle of 0. You see here, I have prepared several other implants. So I zoom a bit out for you so that you can see them. So I have here prepared some other implants in this vial here, or here I have another little one lying on the table. And if I would measure them, and they are also all hydrophilic implants, then for all of them I would get out a contact angle of 0, and I do not know anything has happened on the surface. So this is really useful to have these imaginary contact angles to quantify hyperhydrophilic surfaces. So now what we do is, now we can take out this implant. And now what I want to show you quickly is, if I treat this implant with plasma, what is happening? But for this experiment, I use another type of the implant, because this implant here, you have seen already without any treatment, this was a very, very, very hydrophilic implant. But the other implant that I have here with me on the table, this is not so hydrophilic. So what the tooth doctor will do to activate it before use and put in the customer's mouth, he will use this kind of plasma treatment system. And then inside his office, he will directly before implant it, because plasma effects, they are often short time effects. He will take his implants, take this kind of plasma device, and then he will treat the surface. So I zoom a little bit in with the camera, because this looks really, really nice when the surface gets treated. So I hope we get it also sharp. So I hope you see this a little bit, that blue light is jumping over and we are treating the implant surface with plasma. Yeah? And during this plasma treatment process, the surface is activated and it's becoming more and more polar. And this is then helping us to get the implant better wettable and then more well accepted in the customer's mouth. So since our time is a bit limited and we have also a lot of questions, I want to use some results that I have already made before in order to show you the differences before and after plasma treatment for the imaginary contact angles. So for the live measurement, I want to show you again, you are getting out this kind of curves, and then you are analyzing them automatically by defining some trigger lines, and then you get the slope in between. And then the system is extrapolating these linear lines until they are intersecting with the y-axis. And from this value, we are then getting the mass. And then internally, the system is calculating how high the imaginary contact angles are. Okay. Now, let me quickly get to some slides where I present you these results. So probably I have now also skipped a couple of them. So we completed our first mission. We have made sure we are using pure and clean water. This means our literature value is correct for the surface tension. Then in the next step, I have measured with you one tooth implant. And the tooth implant that I have measured with you, this was a hyperhydrophilic implant. So you have seen contact angle is 0 and a very, very significant imaginary contact angle was measured. Remember again, the higher the imaginary contact angle, the more wettable is the substrate. Now I want to show you a close-up and nice video how the wetting process of a very hydrophilic implant is typically looking like. So let me start this one. So you see the implant is touching the surface and the water is running way before the surface upwards towards the top of the implant. So this is a hyperhydrophilic substrate. Let me go back again. I think this was a little bit fast. So have a look again. It touches the surface and the water runs up like a rocket to the top. Okay, and this means when the water goes up so fast, then the mass, of course, at the implant is also increasing very fast. And this is then leading to that the equation can only be solved by imaginary numbers. Good. You have also seen I have done the plasma treatment of the surface, but we do not do the measurement now again. I just show you the very nice results that we have already gotten. So to tell you a little bit the story before, so these measurements we were doing together with a tooth doctor. So at the moment in each dentistry practice who is implanting this kind of tooth implants, they normally have some UV light-based devices. And inside these devices, you put the little implant, switch it on, and then by UV light, the surface of the implant is activated. So I assume you know UV light, this is very high energy light, and I guess it's partially also leading to oxidation of the surface and making it more rough through this. Then we took implants of the same type and we treated them with this kind of plasma device that you have seen here, the so-called piezo brush. And you can see treating it with plasma for 120 seconds is giving you exactly the same imaginary contact angles like you would get after 5 to 12 minutes of UV light treatment. So at the moment, tooth doctors, they use 12 minutes UV light for the treatment. So you see in 2 minutes with plasma, you can get the same effects, and this kind of handheld plasma machines, they are way cheaper than the comparable UV machines. So this means very, very easily with this method, we can show how the implants, they are changing after being treated with a plasma. You know, for all of these here, you would have gotten contact angles of 0 if you do not use the imaginary contact angles. So you have no chance to study this kind of phenomenon and this kind of treatment processes. And then I also want to show you here the two values on the very right side. So this is an implant that is fairly hydrophilic. And this implants we have also then compared, and you can see, okay, here the advancing contact angle is around 90 degrees. So this means this implant is very, very, very badly wettable. But if you treat it with plasma or also with the UV light, you can get this relatively hydrophobic material to become a hydrophilic material. Okay, good. So I hope this was quite interesting for you, and I hope you understood also the concept of the imaginary contact angles. I want to, before we do the question and answer, I want to go back to one of your questions. So one question was about the correlation between the wettability and the adhesion. And I can tell you these implants here, they are in the so-called Wenzel state. So this means even the cavities on the surface, they will be completely wetted by the water. And in order to prove this, this would mean that there should be a very, very strong adhesion. We have a device that can also help you to do so-called adhesive force measurements. So you would then take the implant, you have a rod, at the end of the rod is a drop of water, and then you put this rod onto the implant and you pull it off again. And like this, you can study and measure the force that is needed to pull off the water droplet. And also here, it's the case. After the plasma treatment, the adhesion is much, much higher, and also the wettability is higher. but this is only the reason because this one is a Benzel state where all the cavities are wetted. So if you are interested in this method, I think for today the time is a bit short, but in the future or something, you just give us a call and then we can also talk together a little bit more about this adhesive force measurements. But for now, we can move on and we go over to the question and answer session, I think. And thank you very much for all of you for your attention. Oops. So this one.
About it. Thank you very much, Sebastian. It was a fantastic demo. So, right. So for the questions that I have, that's we will go through those just in terms of time. There's still quite a few of them, but I think we'll be able to get through them quite quickly. Yes. So for just one thing, I had a few people ask about some additional application notes. That is that the link has been shared in the chat, and also down in the left-hand side, directed towards the application notes. I'm also going to release the slides, so please check the handouts section or the handouts tab for all of those. So those are the slides presented by Sebastian, and then there's some other application notes there. So let me just scroll back to the last question that we had. So we had a couple of questions just asking about how are fibers measured with the tensiometer?
Mm-hmm. So I will explain this on the device because I think it's more easy to do so. So if you want to measure a fiber, it is very, very similar to the implant measurement that we are doing at the moment. So you have to imagine we will also use a similar holder. It is a rod, and this rod at the lower end, it has a little plastics plate. And with an adhesive, we are gluing the fiber to this little plastics plate. So this is for single fiber measurements. Then what we do is we also, like before, mount it in here in our tensiometer, and then the stage goes up automatically. The fiber will be immersed in the water, and the device is recording at the same time the mass over time. So just imagine the implant that is now here on the stick. It can also be a very, very thin fiber, and the measurement is then absolutely the same way. This is for single fibers. If you want to measure fiber bundles, so you know, like a piece of my shirt, for example, then we are using a different type of holder. I show you quickly. This one here. So for fiber bundles, we have this kind of pipes. So you can screw it up on the upper end. And I want to show you. Hey, there's a long screw. So this one is hollow inside, and then you just take my shirt or any other fabric and you stuff it in here. And then you can see there are many, many tiny holes below. Then you are closing your pipe, and with the little wheel here on top, you can very precisely compress it inside. Then you take the whole thing, you remove your single fiber, and you put in this guy here. Hoppala. Good. And then also, like before, it will be done in a way that automatically the stage is moving up until it is contacting the lower end here of this probe. And then through the holes, water by capillary effects is racing up into the fiber bundle. And the guy here is again recording the mass over time. And from the mass increase over time, it's then calculating the dynamic contact angles. Okay. So both single fibers and fiber bundles are possible.
Okay. Excellent. We had a question just asking, Sebastian, are you happy to share your email address for anyone to get in touch with you to ask questions?
Yeah, sure, no problem.
Brilliant. Okay. Let me find that. I'll put that in the chat. So how light in weight can the solid be for measuring? I guess how light of a thread is capable to be measured?
So do I understand this correctly? You want to know how much is the absolute weight of the fiber, for example, that can still be measured? Or if you have a fiber, for example, that is only 1 milligram heavy in weight, is the lamella that is forming at it still heavy enough to be detected?
I believe that's what they're asking. Yes.
Okay, then good. So this tensiometer that we are using here, this has a weight resolution of 0.1 milligrams. So this means if you have a very tiny fiber, for example, it has only a diameter of 10 micrometer, then you can still easily measure it with this device, because the lamella, it will then typically still be a couple of milligrams. So yeah, I would say fibers down to 8 micrometer in outer diameter, they are easily possible to measure with this device. And if they are much thinner, then we have still 1 tensiometer with a more precise balance. This has 2 digits more, and then you can even go down to, I don't know, 5 micrometer outer diameter, and you can then still measure them. So just that you are getting a number.
Brilliant. I had a question there. What do you mean by classical contact angle measurement?
So for contact angle measurement, the classic one is for me, because a contact angle, you know, this is, you have a drop and there is an angle on the side. So classical contact angle measurement for me is the optical method, in fact, where you can really look at it and you do not need a big software or anything. Also with your bare eye, you can see, okay, the angle there should be around 45 degrees or 50 degrees. So this is classical contact angle measurement by optical contour analysis. So here, when you look here at the sample, you have no clue what the contact angle will be. So this one here is dynamic contact angle measurement by a tensiometer. So this I would not call a classical contact angle measurement.
Okay, great. We had another question from Amit here. You assume that the solid material is placed normal to the plane of the liquid. However, in the case of flexible materials such as fiber, how would you measure the contact angles via tensiometer? I think that was already demoed pretty much, but sorry.
Yeah, only one little comment. So, you know, measuring single fibers, this is possible only if the fiber is very stiff. So this means carbon fibers, glass fibers, this is no problem. But if you have organic fibers, like in my shirt, for example, they have a lot of OH groups on the surface. And if you then go and submerge it to water, these fibers are swelling and bending. So this means typically organic fibers, you have to measure them as a bundle, because then it does not matter. But if you have synthetic fibers like glass fibers, carbon fibers or something, then you can still do this kind of single fiber measurements.
Brilliant. Okay, sorry, let me just scroll to the next question. Are liquid densities important in surface energy measurements? I think we already covered this pretty much, but yeah, pretty much not really is basically the is the short of it. So I had a question there regarding the implant. Why 8 millimeters immersion?
Yep, this I have to also show you. Look, so I hope you can see this a little bit. Now it's focusing on my face, but now you can see the implant. So this implant that we are using here, it has a total length of 13 millimeters. But you see here at the beginning, it has around 5 millimeters of a conical section where I do not know the diameter very exactly. And only after 5 millimeters, it's becoming a homogeneous cylindrical surface. And you know, you have seen I had to type in the wetted length, and typically we take the wetted length in an area where we have a cylindrical shape. So this means I need to dip it in at least 8 millimeters so that I have 3 millimeters in this linear area here. But of course, there is still the screw turnings on the surface. So we always just determine the outer diameter here, and we neglect that there is a screw geometry on it.
Brilliant. So got another follow-on question. In general, what determines the immersion depth of a sample in the tensiometer measurement? I think that's, unless there's anything else to add, I think you've pretty much covered that. Okay, brilliant. Thank you. Okay, the measurements rely on calibration of a known sample. Do you have such data in advance, or is it a good idea to simultaneously equip the differential measurement to avoid anything ambiguous? Let me just check. I think there was a simultaneously equip the differential measurement to avoid any ambiguities, I think is what the answer is.
So maybe I comment a little bit on this. So in generally, if the geometry of your sample is very well defined, you can also compare different geometries with each other. However, for the implant, you know, we have these screw turnings on the surface, which also have a little effect. So what I would do is I would only compare the exactly same geometry of the implant, code them in different ways, and then you can very good compare the imaginary contact angles with each others. If you have one implant like this one here and the other one is with very, very big screw turnings and conical over the complete shape, then it's very difficult to compare the numbers with each other because they have so different geometries. So I hope this answers your question.
Okay, we got one there. Do you have to have special software for the imaginary contact angle measurements?
No, it's included in our standard software.
Okay. Yeah. Another one. Why in the de Noy ring method is density needed? What is the relation or equation of density with this?
Okay, this is a good question, but for this, I quickly open one other slide to explain it a little bit to you. Just give me 1 second.
Brilliant.
So this one here, I want to show this here. Okay, so it is important how heavy is the lamella, because our device, the tensiometer, it only measures the weight of the lamella that is hanging at your de Noy ring, for example. And now you can see this is how a typical lamella will look like. And you see it's not symmetric. You see there and there, left side and right side of the wire, the lamella looks different. And the reason is that the de Noy ring, it has a diameter around 2 centimeters. So the left wire is still feeling an effect of the right wire. And this means we are pulling up an additional piece of liquid here. And this additional thing has to be taken account to by the correction factor, the Sudirman-Waters factor, for example. And this factor, it is depending on the radius of the ring, the radius of the wire, and also the densities. So this factor is taking into account that you are pulling up here in the center an additional amount of water just because the wire on left side and right side, they still feel each other, I want to say. So if the ring is big enough, they don't feel each other anymore, and then this would not be needed. But you do not want to measure in a very, very big beaker using huge amounts. So people then have corresponded on using this kind of correction factor and using fairly small rings with around 2 centimeter diameter. Okay, so yeah, this is the equation.
All right. Go on, regarding the imaginary contact angle. If I claim this as a pseudo contact angle, would it be misleading? It's interesting.
So this, I don't know. So what I can tell you, so some people, when I tell them, oh, we can measure imaginary contact angle, then they ask, what is this? So if I would tell them, oh, we are measuring pseudo contact angles, they would give me the same answer probably. So I think, this is a concept, and it is named also in the literature imaginary contact angles. And I would stick with this term because I think if we call it pseudo contact angle, we might confuse other people. They don't know then anymore at all what they are talking about.
Yeah. And just another thing with regard to that, remember, with pretty much with all wettability experiments, it's all to do with what phases are you measuring against, what solids and what liquids. So when we come back to that term of what is the critical surface energy or critical surface tension, so you are in some ways either limited by by the solid surfaces or the liquids that you're using, requiring this this sort of imaginary contact angle. So it's just that the surface energy of the solid is higher than is measurable by sort of standard methods. That's basically what we mean. It's not really, it's not pseudo, it's just not measurable by the other methods that are otherwise able to be used.
I think they summarize it very good. Thank you.
So we got one there. How do we practically determine if a system is in Wenzel state or Cassie-Baxter state?
This is a very, very good question. So the only thing that I can comment on this is basically that with our devices, you can try to measure on one hand the contact angle, on the other hand the adhesive force. And if you have a low contact angle, but still a big contact angle, but the adhesive force is very low, then you can say, okay, it should be a Cassie-Baxter state. If it's the other way around, you should say, oh, it could be a Wenzel state. But with the products that we have, these are products to analyze macroscopic properties. So we do not have an AFM or something. that then can really look deeply into the details. So I would indirectly do it through the force of adhesion.
Okay, so we got three final questions that we could do in this sort of last little bit. So we got, how about adhesion measurement on a completely wetted surface where you cannot detach a water droplet? Sort of a...
So I think in this case, we cannot really determine an adhesive force with our equipment. What we can do is we can, through the contact angles, determine a work of adhesion, for example. So this may at least teach you something, but the classical experiment, straightforward, put a drop on it, pull it off again, the drop will stay on the surface, and then you will rather get the cohesion when you rip the drop apart in the middle or something, but not a pure adhesion. So I would probably try to go for work of adhesion through contact angle and surface free energy analysis.
Okay, final thing, can you use real fluids as opposed to pure water? Just for general measurements. Yes, but I mean, yes, you technically could, but you were basically the whole point of this, as I was saying, it requires knowing things about either the solid or the liquid. So if you were then changing the fluid, you're then not able to, you would need to have a known solid to then measure things about the liquid. So it's either, you have to choose one to get the other effectively. So it all depends on what type of experiment you're trying to define. I guess that's the quickest way to do that. And then final question here. An extreme case of super hydrophilic or super hydrophobic leads to a 0 or 180 degrees as well. Will that be hypothetic ones? Can you comment on the uncertainty involved in measurements as well as in calculations?
Yeah, so maybe a very short comment. So a contact angle of 0 for super hydrophilic surfaces, this is real and can be measured and can also be seen. A contact angle of 180 degrees, this would mean there's basically, if you go in and zoom in completely, there would be 0 contact towards the surface. So I think this is not realistically happening. What I can tell you, if you use an optical device in order to measure contact angles, then the method, it gets more and more inaccurate the bigger the contact angle is. So there is a very nice publication, I think it was from Professor Ras, maybe we can share this also later on. So he is showing the errors that you are making at measuring optically the contact angles. So if you are talking about 170 degrees contact angle, then already from the picture quality, probably the error range is around 2 to 3 degrees. If you talk about something below 120 degrees, then it's much less than 1 degree error from the measurement. If you are even lower, it's very, very super precise. So what I can tell you is, if the contact angle measurement for very, very high degree droplets is not accurate enough anymore, then I would practically go for adhesive force measurements, because they still see a very, very significant difference. Because you can imagine, if you go from 160 to 170 degrees and you compare the volume of the drop and the wetted area of the drop, then there is a huge difference. And this difference you can see in the adhesive force. If you compare now only the absolute contact angles, and at this range you have an error, it can be plus minus 2, then 170 and 175, it's not meaningful anymore. They are basically the same within the error range. But if you would do an adhesive force measurement for these two, you would see a difference by a factor of 2 or even higher, very, very sure, for the adhesive force. So this means, from my side, if you have very, very hydrophobic surfaces, go for adhesive force measurements if you want to still quantify differences, and don't use contact angle measurements. And for all below, go for the contact angles.
Brilliant. So thank you very much, Sebastian. So with that, we'll draw this to a close. So let me just bring up my final slides to share. We've covered all of that. So I would like to just say a very, very big thank you to Sebastian for the demo and for answering the questions and being here today, and just for the support from Data Physics Instruments. We at Surface Ventures wouldn't be able to do any of the great presentations that we bring to you without our partners. So thank you very much. Thank you, Sebastian. And just like to highlight, as I said earlier, you can view our previous webinars at surfaceventures.org. We have our next webinar coming up in a week's time. That should be up on the website a bit later today, but I think the link shared is shared on Surface Ventures LinkedIn page. It's also available on screen at the moment. Thank you all for listening. Thank you for your questions and the great discussions we've had during this this workshop. And with that, I would like to draw the event to a close. Thank you all very much, and looking forward to future workshops with you all. Thanks, Sebastian.
Perfect. Then all of you have a very, very happy day. And a very quick thank you also to my colleague Sanja, because she prepared the presentation and set up everything around. I only did the presentation finally. So also thanks a lot to her. And all of you for attending, and a happy day.
Brilliant. Thanks very much, Sanja.
Bye-bye.
Fantastic. Thanks all. Bye.